let's try to solve this problem here. A 1.50 gram bullet is fired horizontally into a packet of sand. Okay, let's probably try to sketch the situation first. A packet of sand, okay. So this is a packet of sand. And you are sending a bullet, which is 1.50 gram. You are sending this bullet horizontally into a packet of sand. Okay, then they say that the kinetic energy K, which is over here, of the bullet varies with the depth of penetration D. The D here stands for depth of penetration, as shown in the graph above. So what we can see here is that the kinetic energy decreases linearly with depth, means by as the bullet penetrates deeper and deeper into the packet of sand, we can call this the depth of penetration D. As it penetrates deeper into the packet of sand, the kinetic energy will be decreasing. So this kinetic energy decreasing here means by the speed is decreasing as well. So what we can know that is the bullet is actually slowing down through this journey into the packet of sand over here. Okay, sketch the free body diagram of the bullet as it penetrates the packet of sand. Okay, so we are trying to sketch a free body diagram to represent what kind of forces are acting on the bullet when it is in that packet of sand. Okay, so let's try to do it together. So question A, you have your dot representing the bullet. Your axis, you don't need to rotate your axis in any kind. So again, let's ask ourselves the 5 questions. Does the bullet has mass? Yes, it has mass, so therefore it has weight. Is the bullet connected to any rope, strings, or cable? No, it's not connected to any rope, strings, or cable, so there's no tension here. Next, is there any force being explicitly stated in the question or in the diagram? No, the question didn't say that you push the bullet into the packet of sand. It's just fired. So fired means by it comes out from the pistol. So if it comes out from the pistol, it's no longer touching the pistol anymore. So there's no force acting by the pistol on the bullet when it is flying horizontally. Okay, that journey there, the bullet is no longer in contact with the pistol, or no longer in contact with the air or the explosion of the pistol. So in that case, you don't need to consider the force acting by the pistol on the bullet anymore. Okay, so there's no external force involved. 4th question, is there any contact surface? And this is the point where it starts to get complicated. Okay, let's slightly zoom in a little bit and look at the journey of the bullet in the sand. So this is the bullet and it's traveling in the sand, tracing out a path like this. Okay, so you can probably see that there's a lot of contact in between the bullet and the sand. You have contact up, you have contact here, you have contact here, you have contact here. There's a lot of contact here. So how should we simplify the situation? We can actually simplify it into a situation in which there's a lot of contact in the horizontal component, and there's a lot of contact in the vertical component. So we just summarize it into one component of normal pointing in the y component, one component of normal pointing in the x direction. So if we say it like this, we know that the normal in the y component should probably point upwards. Why should it be pointing upwards? It's because if the normal is pointing downwards and the weight is pointing downwards, definitely the bullet cannot be straight anymore. It has to go downwards. It has to curve downwards. But your question says that it is fired horizontally into a packet of sand. So if it's traveling horizontally, that means the bullet is not moving up or moving down. So there's zero possibility for the bullet to be having acceleration upward or acceleration downward. The acceleration has to be 0 in the y component. So if acceleration has to be 0 in the y component, the force upwards and the force downwards must be balanced so that the sum of force in the y dimension is equals to 0. So because of that, you know that the normal has to be pointing upwards in order to balance the weight of the sand so that the sum of force equals 0 for it to fly horizontally into the packet of sand. So that's the y component of normal. But for the x component of normal, we know that the sand is over here touching the bullet in order to prevent the sand from moving further. So the sand is providing a kind of resistance to the bullet from moving further. In that case, we can probably infer that the force or the normal force in the x component should probably be pointing in the opposite direction to the motion, because the sand is blocking the bullet from moving forward. So it has to be pointing in the left direction. Okay, so we summarize all the touching from different angle into one normal in the x component and one normal in the y component. Okay, so let's continue with the fifth question. The fifth question is the surface rough or not? Well, we know that they are touching a lot of surface here. It's very hard to conclude everything, but we can still say that we can still probably guess that there's friction here. And because the object is sliding across the packet of sand, sliding inside the packet of sand, it's very likely that there's friction, and the friction should be in the opposite direction to the sliding. So we can call it Fk. Okay, the bullet is sliding across the sand, right? So there will be friction over here. Okay, but later, if you continue to read the question, you see that there's work done by gravitational force, there's work done by retarding force. Well, you can see that there's a word retarding force over here, which is not represented in any sense by this free body diagram over here. But if you look at this word retard, this word means that you are not helping, you are opposing, you are obstructing. So this retarding force here means by any force that is obstructing the motion of the motion of the bullet in the packet of sand. Because the normal x and the kinetic friction are both the force that retards the motion, they are both opposing the horizontal motion into the packet of sand, we can actually change this x component of normal and the kinetic friction. We can conclude or combine them together and just call them as the retarding force, because these two forces are the one that prevent the bullet from moving further. So we can call it as retarding force. So now we have already simplified the situation to become three forces only, and we can add on extra and saying that the bullet is actually moving in this direction over here. Okay, we are done with it already. Now let's follow through with the second question. Question B, the work done by the gravitational force. So this will be work done by gravity. It will be the weight dot displacement. And if we open it up, this will be mg s cos theta. Okay, the mg, which is the weight over here, is pointing downward, whereas the displacement is pointing to the right. So we definitely know that the angle between them will be 90 degrees. Okay, so the mass is 1.50 gram. We have to change it into kg. Displacement for how far? We know that at the end of the journey, the depth is 0.400. So means by when the bullet reach this point, it will be at rest because there's no kinetic energy anymore. Zero kinetic energy, K final is equal to 0, means by V final is equals to 0 as well. So we can say that at the end of the journey, the bullet actually stops, and at this point, you can know that depth of penetration is 0.400 meter. So you know that your bullet here has traveled a journey of 0.400 meter. And what's the angle between them? Between the weight and the displacement, it's 90 degrees as we mentioned earlier. We know that cos 90 degree becomes 0, therefore the work done by gravity will be equals to 0 joule. So the weight is doing no work on the bullet when it is traveling into the packet of sand. 0 work done. Okay, next question. The work done by the retarding force. Now we are looking at the retarding force. So we can call it as work by force retarding. It will be equals to the retarding force vector dot S. Okay, if you expand it, it will be F retarding as cos theta. F retarding here is how much? We are not sure. Okay, so that's where we stuck. We don't know how much is F retarding. We know the distance traveled is 0.400, and we know that the angle between the displacement to the right and F retarding to the left, the angle between them will be 180 degrees. So we see that we are stuck. Okay, but don't worry too much about it, because we know that they give us a graph of kinetic energy. Of course, this graph is trying to show us the change in kinetic energy throughout the journey. So if we know that this is the change of kinetic energy, we know that the change of kinetic energy will be related to the total work done. So there will be something related to total work done that can be done over here. Okay, so let's write it out. Work total here will be equals to change of kinetic energy. But how do we find work total? We have three forces over here, the Ny, the W, and the F retarding. We have to find the work done by all these forces. So work done by the gravity, work done by the normal, and the work done by F retarding. But what we can see here is both the weight and the normal over here, normal and weight over here, they are both 90 degrees to the displacement. 90 degrees to the displacement. And we know that when it's 90 degrees to the displacement, cos 90 will be 0, and their work done will be equal to 0. So that means by the normal force and the weight here will not contribute any work done to the total work done over here. The work done by gravity and the work done by normal will be equal to 0. Therefore, our work total will later be equals to the work done by F retarding. This is very important because it allows us to make the statement that because work total is also equals to work done by F retarding, work total is also equals to change in kinetic energy due to work energy theorem, we can come to a conclusion and say that the work done by the force retarding here will be equals to delta K. Okay, this is very important because we already have the delta K. We know the final kinetic energy, we know the initial kinetic energy. And from there, we are able to work backwards to find the work done by the retarding force. Okay, I should probably continue it here, make everything in the same page. Okay, so I know that WF retarding over here will be equals to K final minus K initial. We know that K final at the end of the journey, it will be equals to 0. K initial, the initial, when we start the journey, the kinetic energy is 24. So this will be equals to 0 minus 24. And therefore, we know that work done by the retarding force is equals to negative 24 joule. Okay, so if you use a normal conventional method, just Fs cos theta, you face some problem because you don't know the retarding force. But through analysis of the total work done, you see that the total work done is actually the same thing as the work done by the retarding force. And therefore, you can apply the work energy theorem to determine the work done by the retarding force. So that's question C. And question D, they ask you to determine the total work done. And since we know that work total is equals to work F retarding, we can make a statement that work total is actually equals to negative 24.0 joule. Okay, it makes sense that our total work done is equals to a negative value because negative value for total work done means by the change in kinetic energy is negative. Change in kinetic energy is negative means by the object is slowing down, which match what we have said earlier. Okay, so we are done with A to D. Let's continue with E. Determine the average retarding force acting on the bullet as it penetrates the sand. Okay, so they are looking for this value that we are missing just now. But we already have the work done by force retarding and it's negative 24. So because we know that it's negative 24, we can bring it inside this equation to find our F retarding. Okay, so let's try to do it on another page. Question E. You you are aware that work done by force retarding over here is equals to F retarding, the retarding force, multiplied by S multiplied by cos theta. Just now already filled in the value for S. The value for S is the depth of penetration, maximum depth of penetration, which is 0.4. Whereas the cos theta is 180 degree because you are opposing the motion, right? We already know that the work done is negative 24. This is from question C. So now if you do your substitution into a calculator, I believe you'll find that the force retarding over here will be equals to 60 Newton. So this is the retarding force, and technically you should get a positive value. Some might be thinking you should be getting a negative value, but no, it should be a positive value, because if you remember, F here, it's the magnitude of the retarding force. So magnitude of a vector must always be positive. The F and the S must always be positive in the work done equation. What controls the work done, whether it should be positive or negative, is the cos theta at the back. This F and this S here are both magnitude of two vectors, F and S. Because their magnitude, they should always be positive, and that's why this retarding force is correct to be positive. Okay, what controls you to get this negative 24 here? This negative here comes from the cos 180 degree because they are in opposite direction. Okay, so that's question E. Let's continue with question F. Determine the initial speed of the bullet before it enters the packet of sand. You have the initial kinetic energy. They want the initial speed. Kinetic energy and speed, they are related by half mv squared, right? So in order to find the initial speed, you can say kinetic initial is equals to half mv squared, but this v will be the v initial. So if you have the initial kinetic energy to be 24, and you have the mass which is 1.5 gram, you are able to find the initial speed. Oops. And the initial speed here should be equals to 179 meters per second. So this will be the initial speed of the bullet right before it enters the packet of sand. Then you slowly decrease with time as the bullet penetrates through the packet of sand. And when we reach the end of the journey in the packet of sand, the bullet will stop and you reach 0 meters per second for speed and 0 joule for its kinetic energy. Okay, so that's how you solve this question regarding bullet entering horizontally into a packet of sand. Thank you very much.